Okay, then let's start from continuation of yesterday. Gravitation chapter 7 of class 11. I believe I was at around acceleration due to gravity of the earth at topic 7.5. Let's just directly go there. We have done Kepler's 3 laws, the law of orbits, the elliptical orbits, law of areas, where it will cover equal area. It will sweep, the planets will sweep equal areas at equal distance, equal time, where angular moment at all parts of the ellipse is always constant, and universal law of gravitation. Where force is directly proportional to the product of masses. The distance, the square of the distance, is inversely proportional to the square of the distance, and the universal gravitational constant is mentioned. And the force experienced due to multiple forces is the sum of the individual forces, vectorial sum of the individual forces. That gravitation constant was experimentally found out by Cavendish's experiment. Now let's go to acceleration due to gravity of the earth. Acceleration due to gravity of the earth. Earth can be imagined to be a sphere made of a large number of concentric spherical shells. The smallest one at the center and the largest one at its surface. Okay, a point outside the earth is obviously outside of all the shells. If we consider the earth a huge sphere as a number of shells aligned on top of each other, we can consider the center of earth as the smallest shell and the outermost shell the largest. And if we consider a point on the surface of earth or above the surface of earth, then this point will be outside all of the shells. That's what they're saying here. Thus, all the shells exert a gravitational force at the point outside, just as if their masses are concentrated at their common center, according to the result stated in section 7.3. Okay, we saw a few laws before here, these ones, where the force of attraction between a hollow spherical shell of a uniform density and a point mass situated just outside it, then we will consider this hollow spherical shell as a single as a center, as a point concentrated at the center, the mass concentrated at the center, or a point mass. This is the first law. And second kind of thing we consider is the force of attraction due to a spherical shell of uniform density on a point mass situated inside is zero. All the shells exert a gravitational force. Earth's shells exert a gravitational force at the point outside, just as if their masses are concentrated at their common center. The total mass of all the shells combined is just the mass of the Earth. Hence, at a point outside the Earth, the gravitational force is just as if its entire mass of the Earth is concentrated at its center. Okay. For a point inside the inside the earth, normally if it was a hollow shell, then any point inside the shell, the force should be zero. But earth is not a hollow shell. Because of that, there will still be gravitational force at a point inside the earth. This is illustrated in figure 7.7. This is the earth. This is a point inside the earth. Earth's surface, inner earth. This is the depth, the mass m, located at a depth d below the surface of the Earth of mass me and radius re. We treat the Earth to be spherically symmetric. Normally, Earth is not spherically symmetric. There are many mountains, many hills, many uneven surfaces on the Earth, but here we consider it as symmetric. Again, consider the Earth to be made up of concentric shells as before, and a point mass m situated at a distance r from the center. The point P lies outside the sphere of radius r. The shells of radius greater than r, the point P lies inside. Hence, according to the results stated in last section, they exert no gravitational force on mass m kept at the point P. Basically, what they're saying is, if this is the Earth, and let's assume at some point like this, some depth d, there is a point mass m placed here at this kind of depth, at this depth, and the radius of Earth is re. This one's radius is small r. And we know that the second law stated whenever there is a mass placed inside a hollow shell, the force experienced will be zero. But here we saw two laws: the force due to a spherical shell outside and inside. Here is a special case where we use both the laws. Now, if we consider this shell as shell A and these number of shells as shell B, shells B, there are many shells here, it's not hollow. So if we consider a mass here, then according to in the view of shell A, with respect to shell A, this is a point mass inside the shell A. Because of that, according to the first law, the second law, that is the force inside any point inside the shell is zero. The force on point mass m due to mass of Earth in shell A is zero. But if we consider according to this pair, then this point is situated at a point outside it or on the surface. Because of that, we only need to calculate the force on this mass due to this inside B shell. Only this shell matters. That is what NCERT is saying. Again, consider the Earth be made up of concentric shells as before, and point mass m situated at distance r from the center. The point lies outside the sphere of radius r. For the shells of radius greater than r, the point P lies inside. Hence, according to the results stated in last section, they exert no gravitational force on the mass m kept at P. This is the outer shells. The shells with radius smaller than r make up a sphere of radius r for which the point P lies on the surface. This smaller sphere therefore exerts a force on mass m at P as if its mass m is concentrated at the center. Okay, thus the force on the mass m at point P has the magnitude gm mr. M, small m, is the mass of the point mass, basically, which we are keeping at a depth, and capital Mr is the mass of the shell, this shell's mass, excluding the outer shells. This is not considered. This one is not considered. The one red color is considered. These are outer shell. The green is outer shell. The pink color inside is the red shell. Is the actual considered shell. Because due to the green outer shells, the gravitational force at a point M inside is 0. But since considering the red shells here, they do exert a force on this mass because it's on its surface. And force, which is equal to basic force formula, that is gravitational force formula. We assume that the entire earth is of uniform density. That's obviously not true, but we assume it for easier calculation here for our level, and hence its mass is me, mass of earth, is equals to 4 pi by 3 r cube rho. Basically they used, we know that rho is density, rho equals mass by volume, hence mass, which is equals to rho v, the volume of this inner shell only. We consider the volume of the inner shell only, that is 4 pi by 3 r cube e, where me is the mass of the earth, re is its radius, and rho is its density. On the other hand, the mass of the sphere mr of radius r, rho will be same, but r will change, that is the radius. And the volume of the sphere, we know the formula, it is 4 by 3 pi r cube, 4 pi by 3 pi r cube, 4 pi by 3 r cube. That is a formula for a volume of a sphere. That is the formula used here. And force, which is equals to g m m2 4 rho r by 3 r cube by r square mass of sphere is this much, and hence force, which is equals to okay, we will get this equation. Okay, what they did here is mass which is equals to volume into rho, which is same as 4 pi for the radius inside one, 4 pi r cube, 4 by 3 pi r cube rho. Now total earth, mass of total earth is which is equals to 4 by 3 pi r e cube rho, and here if we send this re cube that side, me mass of earth by re cube is equals to 4 by 3 pi rho. Now keeping this equation aside, we know the force formula, that is force equals m1 m2 g m1 m2 by r square, which is same as g m, the radius sphere, this formula, this is a mass here, 4 by 3 pi, 4 pi by 3 rho, let's write r cube by r square outside, and this, if we see here in our equation here, we have the same value. Now substitute that value here, f, which is equals to then g m me by re whole cube into r cube by r square. And basically this r square and r cube will get cancelled. There will be r remaining. F equals g me by re whole cube into r. This will be the formula. And situation where, let's assume it is the mass is situated at the surface, meaning like if this was earth, let's assume the mass was situated at the surface, like this, where r equals re. If it's situated at the surface, r equals re, then f, which is equals to gmme by re whole cube into re. So we'll get it as f, which is equals to gm1me by re whole square. This is the actual gravitation formula itself. We got it back. Now let's go to the textbook again. If the mass m is situated on the surface of the earth, then r equals re, and the gravitational force on it is f equals gmem by r square e. The acceleration experienced by the mass m, which is usually denoted by a symbol g, is related to f, related to force by Newton's second law by relation F equals mg. Thus, the acceleration due to gravity is force by mass. We'll get mm cancel, we'll get gme by re square. Acceleration g is readily measurable. Re is a known quantity. The measurement of g by Cavendish's experiment or otherwise combined with knowledge of g and re enables one to estimate me, that is mass of earth, from equation 7.12. This is the reason why this is a popular statement regarding Cavendish. There is a popular statement regarding Cavendish, that is Cavendish weighed the earth. Okay. Basically from this equation we get Cavendish already found out the value of universal constant, and the radius of earth is a known quantity, and the only unknown variable is mass of the earth. So basically we know gravitational acceleration of earth, which is measurable. Even Galileo measured it using his inclined plane experiments. So only unknown is mass of earth. So after Cavendish found the universal gravitational constant, he basically weighed the earth, basically found out the mass of the earth. Okay, then let's go to the next main topic, acceleration due to gravity. below and above the surface of Earth. On the surface of Earth, we saw that on the surface of Earth, we know the second relation, force equals mass into acceleration, the one of the most famous laws, Newton's second law, force equals mass into acceleration. Here, acceleration is gravity, acceleration due to gravity, so mg, and g, if you want to find out, it is F by m. Force we know from this formula here on the surface of Earth. So we get G, which is equals to G m m e by r e square by m. This m cancel. We will get G, which is equals to G m e by r e square. This is the acceleration due to gravity formula. This is the acceleration due to gravity on the surface of Earth. Now let's go to below and above the surface of Earth, like in the sky and beneath the ground. We saw the force experienced here, the force experienced below the ground. Now let's see acceleration due to gravity. Now let's consider a point mass at a height h. First case is above the surface of the Earth. What is the acceleration due to gravity experienced by a plane that is flying in the sky? That kind of questions. Consider a point mass m at a height h above the surface of Earth, as shown in figure 7.8a. The radius of the Earth is denoted by Re. Since this point is outside the Earth, oops, I have forgotten. Yes, I changed it. Acceleration due to gravity below and above the surface of Earth. Consider a point mass at a height h above the surface of the Earth, as shown in figure 7.8a. The radius of the Earth is denoted by Re. Since this point is outside the Earth, here this is the Earth's surface, this is a point above, this is the radius Re, this is the whole Earth. G at a height h above the surface of the Earth. Its distance from the center of the Earth, if we add up both radius of Earth and the height, we will get the different distance from the center is Re plus h. If f of h denoted the magnitude of the force on the point mass m, we get from equation 7.5, our law here, we will get it as f of h, force at h, is equals to gmem by Re plus h square. Okay, the acceleration experienced by this point, we will get it by dividing this by the mass of the point. Point mass is f of h by m, and we will get it as f g of h, acceleration due to gravity at this point, is gme by Re plus h square. This is clearly less than the value of g on the surface of Earth. That is because why at a height h the value of g will be lesser than at the surface of Earth is because the force of the gravitational force is inversely proportional to the square of the distance. So as the distance increases, the force decreases, and as the force decreases, the gravity also the acceleration also decreases. We will get g minus gme by r2 square for h. G equal gme r square. When we consider an approximate where, let's assume there is a table and we have a rock over the table. As the table compared to the radius of the Earth is very small, we can neglect it. We can neglect the small difference in height and take it as g equals the normal earth value at the surface. That is what they mentioned. G is equals to gme by r square for h very smaller compared to radius of earth. We can expand RHS of equation 7.14. Here we are expanding it. G of h, which is equals to gme by reh plus h square, g of h, which is equals to gm by re square outside. Basically what they did here is, from our knowledge, at the surface of earth we know the formula, and at a height h the force will be, the force due to gravitation will be gm1 me by re plus h whole square, this at some height h. Now acceleration due to gravity is F by m, so we'll get as gme by re plus h square, h whole square, where this m and this m get cancelled. Now if we expand it, g of h, ga, gravitational acceleration due to gravity at height h, gme by a plus b whole square formula, re square plus h square plus 2reh. I don't think that's how they expanded it here. Okay, they just took it as common. There is, I'll explain word. Okay, this is not the one. This is the formula here. G, which is g of h, which is equals to g of, there is no m, gme by re plus h whole square. This we can write it as, we can take re common, gme by re whole square times 1 plus h by re whole square. Basically we are writing it as re plus reh by re cancel, 1 into h, we will get the same thing. Now if we take re in the numerator common, we will get 1 plus h by re whole square and re square. And if h by re is very small value, very much smaller than 1, we can neglect it and directly write it as gme by re square. Let's go back here. Gh, which is equals to, and just one thing here, This is the equation. Let's write the equation we got again. G of h, which is equals to g at height, which is equals to g of me by re square 1 plus h by re whole square. Now, if we see this equation, this is the same equation, the acceleration due to gravity at the surface of Earth, where g surface, which is equals to gme by re square. So substitute this here. G of h is equals to g by 1 plus h by r whole square, or we can write as g into 1 plus h by r whole negative square. This is the formula we got. Okay, we got the formula. It is re square g1 plus h re whole inverse square. For h is very small, use binomial equation. If that is the case, if h by re is a very smaller than 1, we are going to use the binomial expression. Basically, there is a formula. The formula states that if there is an example, I'll give an example. If n plus, if there is an expression a plus n whole power uh, if there is a plus b whole power n, assuming b is very much smaller than 1, then we can write it as a plus nb, where if when b is very much smaller than 1, we can write a plus b whole power n, which is approximately equal to a plus nb. Basically substituting the power here. And similarly, for this case here, where h by r, when it is very small, where h by r is very small, g of h, which is equals to g into 1 by, not 1 by, it is 1 plus h by r whole power minus 2, and h by r is smaller than 1 in such a case. These both are similar here, so we can write g of h, which is equals to g times 1 minus 2h by r. Basically, this minus came here. This is a formula, a trapezium. But that is only for special cases where h by r is very smaller than 1. Let's go back. where we will get this equation 1 minus 2h by Re. Equation 7.15 thus tells us that for small heights h above the value of g decreases by a factor 1 minus 2h Re. If it's very small heights, it will decrease by this factor. Now consider a point mass at a depth d below the surface of the earth. Now above the surface case is over. Let's consider at depth the acceleration due to gravity. At a depth, consider a point mass at a depth d below the surface of the earth. This diagram, not that diagram. Figure 7.8 b here, this diagram here, so that its distance from the center of the earth is Re minus d. Here we are subtracting, here we added. As shown in the figure, the earth can be thought of as being composed of smaller spheres of radius Re minus d and a spherical shell of thickness d. The force on M due to outer shell of thickness d is 0 because of our second law. That is the result quoted in the previous section. As far as the smaller spheres of radius Re minus d is concerned, the point mass is outside it. Hence, according to the result quoted earlier, the force due to the smaller sphere is just as it entire mass of the smaller sphere is concentrated at the center. If me is the mass of the smaller sphere, if ms is the mass of the smaller sphere, then ms by me is equals to Re minus d whole cube by Re whole cube, since mass of the sphere is proportional to the cube of its radius. How we got that is, let's find out. Mass, which is equals to product of volume and density. So mass of earth, ratio of the smaller mass of smaller sphere by total mass of earth, mass of smaller sphere by mass of earth, which is equals to 4 by 3 pi r minus Re minus d whole cube by 4 by 3 pi Re whole cube. These both are same, so they will get constant. So ms by me, which is finally equal to, there is also a rho here, but since it is considering the density of earth, which is considered uniform here, both are same, both will also get cancelled. We will get Re minus d whole cube by Re cube to the ratio of their masses. Let's go back. We didn't go there at all. This is the basically okay. That's why we got this equation here. Since mass of the sphere is proportional to the cube of its radius, there is a diagram here. G, that is acceleration due to gravity at a depth d. In this case, only the smaller sphere of radius Re minus d contributes to G because the outer shell, which considers the point to be inside it itself, so the force due to it is 0. Thus, the force on the point mass M is force at depth d, which is gmem by Re minus d whole square, which is something we got here. Now that is the case, substituting for ms from above, that is from this equation, like we know this is this case, like this is a formula. Basically, force at depth d, which is equals to g MEM by RE minus d whole square, and g at depth d is basically F by M, basically GME by RE minus d whole square, and wait, not ME, it's not ME, MS, not ME, MS, the smaller sphere, not the whole earth, as the outer shell does not contribute to G here. And ms we do not know, but we know the relation here, that is ms by me, which is equals to re minus d whole cube by re whole cube. So we'll get ms, which is equals to mass of earth times re minus d whole cube by re whole cube. Now substitute this in this above equation, we will get it as g at depth d, which is equals to g of me r minus d whole cube by re whole cube times re minus d whole square cube, get cancelled, re minus d is remaining. So g of d, which is equals to g at depth d, which is equals to gme re minus d by re square by re. So basically this again is the acceleration due to gravity at surface, we know. So substitute it here, we will get g at depth d, which is equals to g times of re minus d by re, or we can write it as g at depth d, which is equals to g at surface, which is a very known value, that is 9.8 meter per second, g times 1 minus d by re. This is the formula. Now let's go back here. We'll get Fd, which is equals to gmem re minus d by re whole cube. Okay, and then the acceleration due to gravity at depth d, which is equals to Fd by m. We'll get this much value which we got before, and substituting gme by r square, re square as g, we will get 1 minus d by re, the last equation we got. Thus, as we go down the Earth's surface, the acceleration due to gravity decreases by a factor of 1 minus d by re. The remarkable thing about acceleration due to gravity is that it is maximum on the surface, decreasing whether you go up or down. If we see the Earth, here at word here, if this is the Earth, nope, that is not the Earth. This is the Earth, and g value, g maximum at surface, because all of the Earth all of the mass of the earth is considered here, and this is the minimum distance that a particle can be from the whole of the mass of the earth. If we go down further, as we go down, these layers, these outer layers will get on disappearing as their effect on the mass will keep on reducing. As their effect on the mass keeps on reducing, so since we know force is directly proportional to masses, product of masses, and it's inversely proportional to distance, as the mass keeps on decreasing, here mass decreasing, the force also decreases. But then if we go above the particle, above the earth's surface case, the distance keeps on increasing, distance increasing, force decreasing. So force and acceleration due to gravity is maximum at the surface. Important point, remember. And it goes down by 1 minus d by re as we go towards the depth of the earth. Now let's go to the next main topic, that is gravitational potential energy. We had discussed earlier that notion of potential energy as being the energy stored in the body at its given position. Okay, potential energy is the energy of a body due to its configuration or position. If this position of the particle changes on account of forces, I forgot to change it once again. Okay, gravitational potential energy. We had discussed earlier the notion of potential energy has been energy being stored in a body at its given position. If the position of the particle changes on account of forces acting on it, then the change in its potential energy is just the amount of work done on the body by the force. Okay, if the position of the particle changes on account of forces acting on it, okay, if there are forces, unequal forces acting on a body, obviously the particle should move and change its position. Then when there is a change in its position, the change in potential energy is just the amount of work done on the body by the force. How much this potential energy changed? If it increased, the work done is positive. If the potential energy decreased, then the work done is negative. If there is a force on a body, it's an unequal force, and because of that force, there is a change in configuration of the body. And how do we calculate the work done is, it is according to the potential. The potential energy, if the change in potential energy from initial position to final position, that is the work done. As we had discussed earlier, forces for which the work is done is independent of the path are conservative forces. The forces where the work done does not depend on the path taken or path followed are called as conservative forces. The force of gravity is also a conservative force, and we can calculate the potential energy of a body arising out of this force called the gravitational potential energy. Now let's consider points close to surface of the earth at a distances from the surface much smaller than the radius of the earth. In such cases, okay, we consider first close to the surface of the earth. That is the first point. Second point is at a distance from the surface much smaller than the radius of the earth. Okay, it's close to the surface of the only one point we considered. The force of gravity is practically a constant equal to mg. This is close to the surface of earth, directed towards the center of the earth. If we consider a point at height h from the surface of earth, this is not close to, this is a second point, at a point above the height, a point at height h from the surface of the earth, and another point vertically above it at height h2 from the surface. at one height h1 here. This is the surface of the earth. One height h1, one more height h2. From if we consider a point at height h2 from the surface of the earth, h1 from the surface of the earth, another point vertically above it at a point h2 from the surface. The work done in lifting the particle of mass m from the first to the second position is denoted by W12. From here to when we move it to here, the work done is denoted by W12. Work done formula is force into displacement. Force is mg, that is at heights close to the surface of the earth. So mg times h2 minus h1. If we associate a potential energy WH at a point at a height h above the surface such that WH which is equals to mgh plus W naught, or WG is W naught, where W naught is a constant, and it is clear that W12 which is equals to potential energy at H2 minus potential energy at H1. Okay, let's assume we associate a potential energy WH. The potential energy at a point height at a height h is WH, and this WH which is equals to mgh plus W naught, where W naught is a constant. Then we will get that W12 which is equals to WH2 minus WH1. The work done in moving the particle is just the difference of potential energy between its final and initial positions. Observe that the constant W0 cancels out in equation 7.22. Setting h equals 0 in the last equation, we get WH0 which is equal to W0. H equals 0 means position on the surface of the earth. Thus, W0 is the potential energy on the surface of the earth. If we consider points at arbitrary distance from the surface of the earth, the result just derived is not valid, since the assumption that the gravitational force mg is constant is no longer valid. However, from our discussion, we know that a point outside the earth, the force of gravitation on a particle directed towards the center of the earth. Basically, this is the force at any point, and it is directed towards the center, where me is the mass of the earth, m is the mass of the particle, and r is distance from the center of the earth. We now calculate the work done in lifting a particle from r equals r1 to r equals r2 along a vertical path, or any path in that matter. We get W12 which is equals to gmm by r square dr. From r1 to r2, we will get minus gmem by r1 by, or we can get it as gmem 1 by r1 minus 1 by r2. In place of equation 7.21, we can thus associate a potential energy Wr at a distance such that Wr which is equals to gmem by r plus W1, valid for r is greater than the radius of the earth. So that once again W12 which is equals to Wr2 minus Wr1. Setting r equals infinity in the last equation, we get Wr equals infinity which is equals to W1. Thus W1 is the potential energy at infinity. One should note that only the difference of potential between 2 points has a definite meaning from equation 7.22 and 7.24. One conveniently sets W1 equals to 0 so that potential energy at a point is just the amount of work done in displacing the particle from infinity to that point. We have calculated the potential energy at a point of particle due to gravitational forces on it due to the earth, and it's proportional to the mass of the particle. The gravitational potential due to gravitational force of the earth is defined as potential energy of a particle of unit mass at that point. From the earlier discussion, we learned that gravitational potential energy associated with two particles of m1 m2 are separated by distances. By distance r is given by potential, which is equals to gm1 m2 by r. This is potential, not potential energy. It should be noted that an isolated system of particles will have total potential energy that equals the sum of energies given by the above equation for all possible pairs of its constituent particles. Is an example of the application of the superposition principle. Okay, let's see an example here. Find the potential energy of a system of four particles placed at the vertices of a square of side L. Also obtain the potential at the center of the square. Okay, we need to find the potential energy of the system of four particle charges placed at vertices of a square of side L. We can use the formula n into n minus 1 by 2, where for two systems will three systems we'll get three pairs, and for four system we'll get six pairs. When we consider four masses each of m at the corners of a square of side L, we have four mass pairs at a distance L and two diagonal pairs at distance root 2L, so total of six pairs. Hence WR, which is equals to minus gm square L minus 2 gm square, 4 at vertices and two diagonals here, so that's why we take root 2L. Simplifying this, we will get minus 5.141 gm square by L. As for gravitational potential at the center, potential, which is equals to 4 times of root 2 gm by L, Okay, what they did here is basically the formula is GME m by r. R is root 2L by 2 based on Pythagoras theorem. So we'll get, and we are not considering a mass at this point. The formula, we do not take this one here. The formula is Gm by R. Gm by R. So Gm by root 2L by 2. This 2 goes up to Gm by root 2. This we can simplify by rationalization. We will get root 2 Gm by L, and this is for a single vertex. For 4 of them, we just add them. So minus is there in the formula. Into 4 or plus 4 times, we will get minus 4 times of root 2 Gm by L. Let's go to the next main topic, that is escape speed. If a stone is thrown by hand, actually wait a second, let's take a 5 to 10 minute break before that. Okay, then let's continue. Escape speed. If a stone is thrown by hand, we see that it falls back to the earth following a projectile motion. Of course, using machines, we can shoot an object with much greater speeds, and with greater and greater initial speed, the object scales higher and higher heights. A natural query that arises in our minds is the following: can we throw an object with such high initial speeds that it does not fall back to the earth? It just leaves to space. The principle of conservation of energy helps us to answer this question. Suppose the object did reach infinity and that its speeds there was v final. The energy of an object is the sum of potential and kinetic energy, as before W1 denotes that gravitational potential energy of the object at infinity. The total energy of the projectile at infinity then is, well, let's read that again. Suppose the object reaches infinity and its speed at infinity is v final. The energy of an object is the sum of potential and kinetic energy. As before, work W1 denotes the gravitational potential energy of the object at infinity. The total energy of the projectile then at infinity is the sum of gravitational potential energy plus kinetic energy. W1 denotes the gravitational potential energy at infinity, and it is half mv square, that is kinetic energy, the formula of kinetic energy. If the object was thrown initially with a speed of v initial from a point h plus re from the center of the earth, re is the radius of the earth, its energy was eh plus re half mvi square minus gmme h plus re plus w1. This negative is already in the formula, so we kept it here as well. The principle of by the principle of conservation of energy, this 7.26 must be equal to 7.27. Both should be equal at the infinity as well as at somewhere at the surface of the earth or some point above the surface of the earth. So where w1 w1 get cancelled, mv initial square by 2 minus gmeh plus re, which is equals to mvf square by 2. The RHS is a positive quantity with a minimum value 0, and so must be LHS because right side is positive, left side is also positive. Thus, an object can reach infinity as long as V initial is such that mv initial kinetic energy minus potential energy, or the sum of initial kinetic energy and potential energy, should be greater than 0. Only in such a case can it reach infinity. The minimum value of V1 corresponds to the case when LHS of the equation equals to 0. The minimum is when, if finally the kinetic energy is becoming 0, it is converting all the kinetic energy into potential energy, that is at infinity, and it becomes 0, total energy becomes 0. So basically, then the minimum kinetic energy will be equal to 0. That means half mv initial square is equals to gme by h plus re. If the object is thrown from the surface of earth, h equals 0, then we will get that the initial minimum escape speed is equals to root of gme by re. and by multiplying Re, we will get into Re root Re, and this whole thing will become G. So we'll get final equation as root of 2G Re using relation G equals GME by Re square. Using the value of G and Re numerically, we know the values of G as well as Re. It does not depend on mass here, it seems. By using the value of acceleration due to gravity as well as radius of the earth, numerically, the minimum escape speed, which is 11.2 kilometers per second, is not per hour, it is 11.2 kilometer per second. This is the speed, minimum minimum escape speed for any body irrespective of the mass. This is called the escape speed, sometimes loosely called the escape velocity. Equation 7.32 applies equally well to an object thrown from surface of the earth, surface of the moon with G replaced. Okay, this doesn't need to be only earth. If we replace the acceleration due to gravity on the surface of moon and radius of moon, we will get the escape velocity of the moon as well, with G replaced by acceleration due to moon's gravity and its surface, and Re replaced by radius of the moon. Both are smaller than their values on earth, and the escape speed for moon after substituting the constant should be 2.3 kilometers per second, about 5 times smaller. This is the reason that moon has no atmosphere. Gas molecule it formed on the surface of the moon having velocities larger than this will escape the gravitational pull of the moon. Now let's see an example here. Two uniform solid spheres of equal radii r but mass m and 4m have a center to center of separation 6r as shown in figure 7.10. The two spheres are held fixed. A projectile of mass m is projected from the surface of sphere of mass m directly towards the center of the second sphere. Obtain an expression for the minimum speed of v of the projectile so that it reaches the surface of the second sphere. It must escape the gravitational pull of the first sphere. Thus, projectile is acted upon by two mutually opposing gravitational forces of two spheres. The neutral point N is defined as position where the two forces each can cancel each other out. If this ON is equal to R, GMM by R square, which is equals to 4GMM by 6R minus R square, where we'll finally get R, which is either equal to 2R or minus 6R. But minus 6R does not concern us in this example. Therefore, we will use R equals 2R. It is sufficient to project the particle with a speed which would enable it to reach to n. After reaching that, it will have a constant speed n. Due to that sphere acting on it towards it, so it will continue to move in that direction. Thereafter, the greater gravitational pull of 4m would suffice. The mechanical energy at the surface of m is E initial, which is equals to half mv square minus the total initial energy half mv square. If it is moving, minus gmm by r minus 4 gmm by r. At neutral point, the speed approaches zero. The mechanical energy at n is purely potential. En, which is equals to minus gmm by 2r minus 4 gmm by 4r. From the principle of conservation of mechanical energy, we'll get m cancel. Both should be equal at E initial and at E neutral point. Both should be equal from the principle of conservation of mechanical energy. M will get cancelled, and from solving this equation, we will get that V should be approximate V square, which is 2 gm by r, and V should be approximately 3 gm by 5r whole root. A point to note is that the speed of the projectile is 0 at n, but it's non-zero when it strikes the heavier sphere 4m. The calculation of the speed is left as an exercise to the students. That we can calculate using acceleration due to gravity. The total acceleration due to gravity at the next point that as well we can, I believe, calculate using conservation of mechanical energy. This one we can solve with two spheres of same radius having same radius of r. Six r is this distance. This is r. This is r. Till this point is the neutral point. This is the neutral point. At neutral point, gm m by the mass of the projectile by r, if we consider this distance as r, which is equal and opposite to 4 gmm by 6r minus r. There should be square here as well. Gmm cancel. 4r square is equals to 36r square. No, wait, we don't need to do that. 6r minus r whole square. We can take 2r whole square. We can write 4r square as 2r whole square, which is equals to 6r minus r whole square. This cancel. We'll get 3r, which is equals to 6r, or we should take it as plus or minus, but since 2r doesn't matter, we'll get r, which is equals to 2r. Neutral point is at a position 2r. Now initial mechanical energy, which is equals to half mv initial square minus gm mm by r minus 4 gmm. This is not r. This should be this distance, that is 2r, and if this distance is 2r, then this should be 4r, and E final, that is E at n, neutral point, should be, kinetic energy should be 0. Only potential energy gmm. Wait a second, this is not r, 2r, wait a second. This is simply r because it is at the surface, and this should be 5r, is initial, so and at n, at neutral point, we should take it as 2r minus 4 gmm by, this will become 4r. Now, due to conservation of mechanical energy, both should be equal, where half mv initial square, which is equals to minus gmm by r minus 4 gmm by 5r, which is equals to minus gmm by 2r minus 4 gmm by 4r. If we take this cancel, these both are same, cancel, then we will get half mv square initial, which is equals to minus gmm by 2r plus 4 gmm by 5r, which is equals to minus 5 gmm plus 8 gmm by 10r. We can write this as 3 gmm by 10r, which is equals to half mv initial square. M we can cancel here. This 2 will go that side. V initial, which is equals to 6 gmm by 10r. We can write as 2 3s are, 2 5s are. V initial, which is equals to root of 3 gmm by 5r, not mm. Which is the same answer which we got in the textbook. As for if you want to calculate the speed at when it strikes the heavier sphere 4m, then as well initial kinetic energy will be the final kinetic energy in this case minus gmm by 2r minus 4 gmm by 4r. Okay, now E final, when it's supposed to strike the sphere, there should be a kinetic energy EmV final square. There should also be a potential energy minus GMM by 5R minus 4GMM by R. Now both of them should be equal. Equating them, we will get it as, we can cancel mm directly, mmm. We'll get it as minus gm by 2r minus 4, or directly I'll write it as gm by r, 4 cancel here, which is equals to half, there's no m, v final square minus gm by 5r minus 4gm by r. When this gets here, this and this will become 3, and we will send it this side. We will send this one this side, minus gm by 2r plus 3gm by r, which is equals to half vf square minus gm by 5r multiplying this by 2, we can get it as 3 minus, wait, not 3, 6 gm minus gm by 2r. This gm will shift here, gm by 5r, which is equals to half vf square. This will become 5gm by 2r plus gm by 5r, make LCM 25gm plus, not 25, actually it is 25gm plus 2gm by 10r, which is equals to half vf square, 27gm by 10r, which is equals to half vf square, 1s are 5s are, so approximately we will get vf, which is equals to root of 27gm by r by 5r, 27 by 5, which is 5.2 something like that, no, 5.4, 5.4, or we can keep it like this. This is the final velocity when the projectile is just about to hit the hard sphere or the 4m sphere. Let's go back to reading the textbook. Okay, the calculation of the speed, that is when it strikes the heavier sphere, that is left to the students. Okay, I did it. Earth satellites. Earth satellites are objects which revolve around the Earth. Okay, their motion is very similar to the motion of planets around the Sun, and hence Kepler's law of planetary motion are equally applicable to them. Satellites revolve around the planets similar to how planets revolve around the sun. Because of that, Kepler's law, which were originally for planets, are even applicable for the satellites. That's what they're saying here. In particular, their orbits around the Earth are circular or elliptic. Moon is the only natural satellite of Earth with a near circular orbit with a time period of approximately 27.3 days or 30 days, which is also roughly equal to rotational period of the moon about its own axis. This is also roughly equal to the rotational period of the moon around its own axis. Since 1957, advances in technology have enabled many countries, including India, to launch artificial Earth satellites for physical use in fields like telecommunication, geophysics, and meteorology. We will consider a satellite in a circular orbit of a distance RE plus h from the center of Earth, where RE is the radius of Earth, if m is the mass of the satellite and v is its speed, the centripetal force required for this orbit for a near circular orbit is mv square by r. For the radius here, the position vector here, position vector's magnitude RE plus h. Directed towards the center. This centripetal force is provided by the gravitational force, which is provided by the gravitational force. Why any kind of circular motion? If the satellite is moving in a circular motion, the force centripetal force for this circular motion is provided by some kind of force. There must be a centripetal force, so that otherwise there is no circular motion. And this circular motion is due to a centripetal force known as gravity. Because obviously there is no other force acting on the moon or the naturals or the other satellites which revolve around the earth. F, which is equal to gmme by re plus h whole square, where me is the mass of the earth. Since both of them are equal, this is also centripetal force, this is the centripetal force, we will get equating RHS of equation 7.33 to 7.34, and cancelling out m, irrelevant of the mass of the satellite, we will get v square, which is equals to gme by re plus h. Thus, v decreases as h increases, inversely proportional. Higher the height, lower the velocity to maintain the orbit. From equation 7.35, the speed v for h is equals to 0 is v square h equals 0 gm by re gre, where we have used the relation gm by re square. In every orbit, the satellite traverses a distance 2 pi re plus h with speed v. Its time period therefore is time period which is equals to 2 pi r by t, which is equals to v. So just shifting it that side. Velocity we know we substituted our velocity from previous equation, basically this one here. On substitution of the value of v from equation 7.35, squaring on both sides, we get the square of time period, which is equals to kre plus h cube, which is Kepler's third law, where the square of time period is directly proportional to the cube of the radius or the distance, where k is a constant 4 pi square by gme, which is Kepler's law of periods. As applied to motion of satellites around the Earth, for a satellite very close to the surface of Earth, h can be neglected, and in comparison to re, hence for such satellite, t is t naught, where t naught, which is equals to 2 pi RE by G root of, if we substitute the numerical values, we will get T naught, which is equals to 85 minutes. When H is almost negligible, roughly we will get it as 85 minutes. That is for a satellite very close to Earth. Very close to Earth meaning its height is very small compared to radius of the Earth, which is 6,400 kilometers. And for such a satellite, the approximate time period is approximately 85 minutes. Moon takes 27 days to revolve around Earth, whereas a satellite which is very close to Earth takes only 85 minutes. Very fast. Anyways, example 7.5, or let's derive this once before. Basically, centripetal force formula, which is equals to mv square by re plus h, the centripetal force. Gravitational force formula, which is equals to gmem by re plus h whole square. Gravitational force formula, equating them both, will get gmem by re plus h whole square, which is equals to mv square by re plus h. This cancel, cancel. So we will get that v square, which is equals to gme by re plus h. Now if you want to calculate time period, or before that, a simpler formula for this, when h is approximately equal to 0, then v square, which is equals to gme by re, which we can write as gme r square into re, where this will become g. V square will become GRE, whereas V will become root of GRE. This is for H is negligible. But if H is not negligible, then we can write V square is equals to GME by RE plus H. And this we can take RE common, or basically we can write RE plus REH by RE into 1 basically. Now we take RE common, RE into 1 plus H by RE, radius of Earth. So V square, which is equals to GME by RE into 1 plus H by RE. Now this we can write as GME by RE square into RE by 1 plus H by RE. This will become G, where G into GRE 1 minus H by RE equals velocity if H by RE is smaller than 1. If not, we need to write it as V equals root of GRE by or into 1 plus H by RE whole power minus 1. This is the velocity for satellite. The velocity the satellites needs to maintain to go in a circular orbit. Now let's calculate time period. We know that V equals 2 pi r by time period, or in this case it is 2 pi r re plus h. This is the time period. So time period, which is equals to 2 pi re plus h by v. V value we know, that is, we will use this equation, re plus h, v which is equals to root of gme by re plus h, t which is equals to 2 pi re plus h by gme by re plus h 1 by 2 whole power 1 by 2 whole power 1 by 2. I just split it for the denominator and numerator. This is the formula here, and for v alone it is root. This will go up. Time period, which is equals to 2 pi re plus h into re plus h whole root by gme whole root. We'll get it as t equals 2 pi re plus h whole power 3 by 2. 1 plus 1 by 2 is 3 by 2 by gme. This is the time period here. The mass of moon doesn't matter, only the mass of earth matters. And let's assume we squared the both sides. We will get t square, which is equals to k re plus h whole cube. T square directly proportional to r cube. Kepler's third law. Here we can see where k is the remaining things which are not mentioned here. K, we need to write k, which is equals to 4 pi square by gme. This is k value. It's a constant basically, because 4 is constant, pi is constant, universal gravitational constant, mass of earth obviously constant. Now if we consider time period, where h is approximately 0, then let's solve. We'll get t which is equals to 2 pi root of re plus 0 whole cube we'll get as t which is equals to by root of GME we can write as root of RE whole square into RE by GME. We know that G is equals to acceleration due to gravity at the surface, GME by R square, and this is basically inverse of it, so we can write it as T which is equals to 2 pi root of RE by G. This is the formula for time period where h is approximately equal to 0, where it is very small, where we neglect it, that's all. It's not at the surface of Earth. It is at some distance above the surface of Earth, where this distance is very small, minute compared to the radius of the Earth. Now that's how we got all the equations on the textbook shown above. That is very few. Okay. Numerical values here, we will get this as 9.8, okay, and we will get it as 85 minutes approx. Now let's see the example here. They are saying that the planet Mars has two moons, Phobos and Deimos. Phobos has a period of 7 hours and 39 minutes and an orbital radius of 9.4 into 10 power 3 kilometers. Calculate the mass of Mars. Okay. Basically here we have the formula right here. They are asking instead of mass of Earth, here we take it as mass of Mars. Assume that Earth and Mars move in circular orbits around the Sun, with the Martian orbit, that is the Mars orbit, being about 1.52 times the orbital radius of the Earth. What is the length of the Martian year in days? This is also a time period question. Okay, this is the first answers. We replace Earth mass by Martian mass m, not Sun's maybe. Okay, then anyways, we will get this equation. This is the equation. Now we substitute the values here. Mass of Mars, we will get approximately, which is equal to 6.48 into 10 power 23. We have all the values, we just need to substitute. Then for the assume the Earth's Mars move in circular orbit, that question about what is the length of Martian year in days, time period, basically we know formula, Kepler's law, t square directly proportional to r cube, so t square m, basically this one we will get that one, because when we apply a constant here, that is k, we get t square by r cube, which is equals to k. Since t square by r cube is constant, we get this equation when we take t1 square or t Mars square, radius Mars, which is equals to, we can equate it to t2 square by r2 square to cube, then both will be equal. R will go that side. This R, this T1 will come this side. We will get R, this one. This equation here. Kepler's law coming to our help. Where RES is the Mars-Sun distance and RES is the MS is the Mars-Sun distance and RES is the Earth-Sun distance, where time period is approximately, we'll get it as, after solving, you'll get it as 1.52 by whole power 3 by 2 into 365, that is same as 684 days. We note that the orbits of all the planets except Mercury and Mars are very close to being circular. Only Mercury and Mars orbit are not circular, but other planets mostly circular orbit. For example, the ratio of semi-minor and major axis of Earth is 0.9 and very close to being 1. Now let's go to the next example. Okay, we should weigh the Earth, it seems. Weighing the Earth. You are given the following data: G, which is equals 9.81 meter per second square. The radius of Earth, which is 6,400 kilometer, or exactly we take it as 6.37 into 10 power 6 meter. The distance to the moon, R, which is the moon's orbit, 3.84 into 10 power 8 meter. And the time period of the moon's revolution is 27.3 days. Obtain the mass of the Earth in two different ways. Okay. Now, since they have given 27.3 days, we can obviously use the time period formula. We will get the mass of the Earth directly in the formula, just like how we took Phobos and Mars for whatever it was, the moon of Mars. We calculated the mass of the Mars. We weighed Mars there. Now, here, same formula, we can weigh the mass of Earth here as well. And one more method, they said two different methods. The second method, they provided acceleration due to gravity at the surface. We know that Cavendish used this method to weigh the Earth, that is mass of Earth here. Basically, he used the formula, our most commonly used formula here, GME by RE whole square, which is equals to G. He shifted this one this side and this one this side. We will remain mass of Earth here, and we will get it as 5.97 into 10 power 24. We don't need anything like mass of moon or radius of moon. This is the easiest method. Then we will use Kepler's laws here, not directly Kepler's laws, but our time period formula here. Then as well, we will get mass of Earth should to be around 6.202 into 10 power 24 kg. Well, there is a slight difference here, but it is approximate. Almost the same answer we will get. The difference between them is being less than 1%. Now let's go to the next example. Express the constant k of equation 7.38. This value here, this is a k equals 4 pi square by GME. Express in days and kilometers. Given k equals 10 power minus 13 second square per meter cube. The moon is at a distance of 3.84 into 10 power 5 kilometers from the Earth. Obtain its time period of revolution in days. Okay, we know the formula, t square, which is equals to k into r cube. They have given us re plus h whole cube. They have given us k value. They have given us k value. They have given us h value. We know the re value. We need to find t value. We will directly get it as 27 days. Note that equation 7.38 also holds for elliptical orbits. If we replace Re plus H by semi-major axis of the ellipse, that will then be at one of the foci of the ellipse. Now, after some solving, let's go to the last topic, that is energy of a satellite, and then the summary. Let's do it. Energy of an orbiting satellite. Topic, last topic, but not the least topic. Energy of an orbiting satellite using equation 7.35. Which is basically this equation here, right here. Yes, this one here. This is the velocity of the satellite that is to be maintained for it to move around in a circular orbit. Using that equation, the kinetic energy of the satellite in a circular orbit with speed v is k equals kinetic energy equals half mv square, v square we know, substituted gmme by 2 re plus h. We have m here. Considering gravitational potential energy at infinity to be 0, the potential energy at distance r plus h from the center of the earth, potential energy will get as minus gmme by re plus h. Kinetic energy is positive, whereas the potential energy is negative. However, in magnitude, kinetic energy is half the potential energy, so the total energy okay, why we say it is half the potential energy is because here if we see, if we consider gmme by re plus h as x, here it is x by 2. X by 2 is kinetic energy, and here minus x is potential energy. So if we add them both, we will get it as minus x by 2. That is what we got here. The total energy of the satellite, the sum of potential and kinetic energy, should be negative of the potential energy, is equals to negative of the potential energy. The total energy of an circularly orbiting satellite is thus negative, with the potential energy being negative but twice in magnitude of the positive kinetic energy. When the orbit of the satellite becomes elliptical, both kinetic energy and potential energy vary from point to point. They get interchanged. Basically, the total the total energy at all the points of the elliptic orbit is conserved. It will be same basically, but at different radius, the potential and kinetic energy keeps changing. As the potential energy decreases, the kinetic energy increases. As the satellite moves into the semi-major axis, or the basically the longer axis, the potential energy reduces, and thus the speed of the satellite will increases. And when it comes closer and the potential energy increases, the kinetic energy will decrease, but it will be conserved. The total energy which remains constant is negative, as in the circular orbit case. This is what we expect, since as we discussed before, if the total energy is positive or 0, the object escapes to infinity. If we saw before that, if the total the escape energy for infinity is that the total energy should be greater than 0, greater than or equal to 0. If it is equal to 0, the final kinetic energy at infinity should be equal to 0. If it is not equal to 0, then it should be greater than 0. The total energy, if only if the total energy is greater than 0, will the object escape to infinity. But here, in this case, in our case, we don't want the satellite to escape into infinity, but keep revolving around the Earth. So in such a case, the total kinetic energy will be uh, less than zero, so that it will keep revolving around the Earth. The escape speed we calculated using mechanical energy, where mechanical conservation of mechanical energy, where the kinetic energy at infinity will be zero. Let's see that again. Escape speed here. At initial, V initial should be equal to V final. As long as it is greater than zero, it will escape to infinity. What this statement 7.30 tells us is that the total kinetic energy required to escape for the potential to become zero. Okay, then let's go back. Satellites are always at finite distance from the Earth, and hence their energies cannot be positive or zero. Now let's say an example given here. A 400 kg satellite is in a circular orbit of radius 2 RE about the Earth. How much energy is required to transfer it into a circular orbit of radius 4 RE? What are the changes in the kinetic energy and potential energies? Okay, we need mechanical energy conservation here. Initially, the energy should be minus GMEM by 4 RE. This is a basic formula. The total energy should be sum of kinetic and potential energies. Kinetic energy is positive GMEM by 4 RE. Potential energy is minus GMEM by 8 RE. No, 2 RE. Because of that, it will become minus GMEM by 4 RE. That is the total energy. And finally, when the radius is doubled, we just double it here. EF is equals to minus GMEM by 8 RE. The change in total energy should be, we should just E final minus E initial. Basically added, the total change in energy is, it gained half of the energy. It became, basically for it to reduce, the magnitude of the energy here reduced. Magnitude reduced, but as it was in minus sign, the energy, the total energy of that actually increased. It actually doubled. Where the change in energy is equals to GMEM by E8 RE is equals to GME R square M RE by 8. This is the total gain in energy, the total difference in energy. Basically, they took GME by RE square common outside, and they took gravitation acceleration due to gravity on the surface of Earth. For simpler calculations, I believe, we will get it as approximately 3.13 into 10 power 9 joules. The kinetic energy is reduced and it mimics delta E. The initial kinetic energy was this much, but it got reduced. but the potential energy has increased. Namely, delta K, which is equals to K final minus K initial, which is basically the total energy did not change, but kinetic energy reduced and potential energy increased. Minus 3.3 into 10 power 9 joule. The change in potential energy is twice the change in total energy, namely delta V, which is equals to V final minus V initial, which is equals to minus 6.25 into 10 power 9 joule. Okay, then let's see the summary. Summary here. Newton's law of universal gravitation states that gravitational force of attraction between any two particles of masses m1 and m2 separated by distance r has a magnitude F equals g m1 m2 by r square. Gravitational law, where g is the universal gravitational constant, which has a value 6.672 into 10 power minus 11 Newton meter square per kg square. If we have to find the resultant gravitational force, this is the superposition theorem acting on the particle m due to a number of masses m1, m2, mn, etc. We use the principle of superposition. Let F1, F2, Fn be the individual forces due to m1, m2, and mn, each given by the law of gravitation from the principle of superposition. Each force acts independently and uninfluenced by the other bodies. Resultant force Fr is then found by the vector addition Fr, which is equals to F1 plus F2 plus dash 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 Fn. Summation of n I equals 1 F initial, where the symbol sigma stands for summation. This is vectorially added. Now let's go to Kepler's laws here. Kepler's laws of planetary motion state that all planets move in elliptical orbits with the sun at one of the focal points. The radius vector drawn from the sun to the planet sweeps out equal areas in equal time intervals. This follows from the fact that force of gravitation on the planet is central and hence angular momentum is conserved. The square of the orbital period of the planet is proportional to the cube of the semi-major axis of the elliptical orbit of the planet. The period t and the radius r of the circular orbit of the planet about the sun are related by t square, which is equals to 4 pi square gms r cube. This is the relation we derived at the last, but they gave it in Kepler's law here, where this is the k value, where ms is the mass of the sun. Most of the planets have nearly circular orbits about the sun except Mercury and Mars. For elliptical orbits, the above equation is valid if r is replaced by a semi-major axis, that is a. The acceleration due to gravity, that is at a height above the Earth's surface. We also calculated this. G of h, we just add h plus h whole square, but do not forget the square. GME, this we take r is common, and for h very small to r, we use the binomial expression like this. G at a h, when g is at h equals 0, then we get GME by r square. And then at depth d below the Earth's surface, the outer shell's attraction or force will become 0 inside the outer shell's hollow surface. You will get the equation to be something like this. This G0 represents the acceleration due to gravity at the surface of the Earth. The gravitational force is a conservative force and therefore a potential energy function can be defined. The gravitational potential energy associated with two particles separated by a distance r is given by V equals minus G m1 m2 by r, where V is taken to be 0 at r equals infinity. The total potential energy for a system of particles is sum of energies for all pairs of particles, with each pair represented by a term of the form given by the above equation. This perception follows from the principle of superposition. If an isolated system consists of particles of mass m moving with a speed v in the vicinity of a massive body m, the total mechanical energy of the body is given by E, which is equals to half mv square minus gmm by r. That is, the total mechanical energy is the sum of kinetic and potential energies. The total energy is a constant of motion. If m moves in a circular orbit of radius of a about m, where m is much greater than small m, the total energy of the system is E, which is equals to minus gmm by 2a. That is a satellite. This is a satellite formula basically, with the choice of the arbitrary constant is a potential energy given in the system point 5 above the total energy is negative for any bound system. That is, one is which the orbit is closed, such as an elliptical orbit. The kinetic and potential energies are kinetic energy, which is gmm by 2a minus gmm by a. They escape speed from the surface of the earth, which is root of 2 gme by r, or root of 2 GRE, and has a value of 11.2 km per second. A particle is outside a uniform spherical shell or a solid sphere with spherically symmetric internal mass distribution. The sphere attracts the particle as though the mass of sphere or shell were connected in the center of the sphere. A law: if a particle is inside a uniform spherical shell, the gravitational force on the particle is zero. If a particle is inside a homogeneous solid sphere, the force on the particle acts towards the center of the sphere. This force is exerted by a spherical mass interior to the particle. Now physical quantities. Gravitational constant here, value we know. Gravitational potential energy represented by V of R. We know it's joule, energy is joule. Gravitational potential represented by U of R, joule per kg. Gravitational intensity, E or G, will basically gm by r square. It's a vector. Now points to ponder. In the considering motion of an object under the gravitational influence of another object, the following quantities are conserved. Angular momentum, that's the reason where the ellipse, like when we consider the Kepler's law here, there, the at all points of the ellipse, the angular momentum is conserved because they are moving in a circular path or an elliptical path, and the total mechanical energy will also be conserved, but linear momentum is not conserved. Angular momentum conservation leads to Kepler's second law, however, that is the area is equal. However, it is not special to the inverse square law of gravitation. It holds to any central force. In Kepler's third law, that is T square is directly proportional to R cube, the constant Ks is the same for all planets in circular orbits. This applies to satellites orbiting the Earth. An astronaut experiences weightlessness in a space satellite. This is not because the gravitational force is small at the location in space. It is because both the astronaut and the satellite are in free fall towards the Earth. Okay, they're saying that a space satellite, is basically revolving around the Earth. This is free falling, a continuous free fall. And at free fall, we experience weightlessness. The gravitational potential energy associated with two particles separated by a distance r is given by V minus gm1 m2 by r plus constant. The constant can be given any value, it can be 0 as well. The simplest choice is to take it as 0. With this choice, we will get a much simpler value, V equals minus gm1 m2 by r. The choice implies that V equals 0, r at infinity. Choosing the location of 0 of gravitational energy is the same as choosing the arbitrary constant in the potential energy. Note that the gravitational force is not altered by the choice of this constant. The total mechanical energy of an object is the sum of its kinetic, which is always positive, and the potential energy related to infinity. We presume that potential energy of an object at infinity is 0. The gravitational potential energy of an object is negative. The total energy of a satellite is negative, otherwise it will escape to infinity. Commonly encountered expression mgh for the potential energy is actually an approximation to the difference in the gravitational potential energy discussed in the point 6. Although the gravitational force between two particles is central, the force between two finite rigid bodies is not necessarily along the line joining their center of mass. Finite rigid bodies, we are not talking about point masses. Point masses will always have a gravitational force along their center, but two rigid bodies will not always have it toward the center. For a spherically symmetrical body, however, the force of particle external to the body is as if the mass is concentrated at the center. For a spherical body, this force is therefore central. For a symmetric, uniform spherical object, only then it will be towards the center. The gravitational force on a particle inside a spherical shell is zero. However, unlike a metallic shell, which shields electric forces, the shell does not shield other bodies outside it from exerting gravitational force on a particle inside. Gravitational shielding is not possible. This we will see in class 12 electric forces or electric fields chapter. We will see that later. Okay, then with that, gravitation revision has completed. Bye.